Okay, welcome everyone. And if you are still at the back, there are still some seats available, particularly up the front, and there's a row of 3 here. So feel free to make your way down and take a seat. I want to welcome everyone to the Aad van, and I'm going to say it correctly, and you can tell me if I've got it right, Ballegooijen. Is that right? The Van Ballegooijen Memorial Lecture. As Director of the Center for Astrophysics, Harvard and Smithsonian, I'm really honoured to lead the community here dedicated to exploring the universe and mentoring the next generation of scientific leaders. This lecture celebrates a colleague who exemplified that mission throughout his remarkable career. Dr. Aad van Ballegooijen was a pioneering solar physicist and whose decades of research transformed our understanding of the sun's magnetic fields, the solar wind, and also coronal heating processes that shape space weather and impact the Earth. His innovative models bridged theory and observation, enabling scientists worldwide to simulate solar phenomena with unprecedented accuracy. Aad's contributions to instruments like the UVCS spectrometer on SOHO provided critical insights into coronal mass ejections and solar streamers. Equally important was his devotion to mentorship. Aad guided students and postdocs across the globe, offering both intellectual rigor and personal support. His quiet leadership and collaborative spirit earned deep respect throughout the international solar astronomy community. And even in retirement, he continued advancing models of solar wind acceleration and turbulent heating, leaving a legacy that endures through the scientists that he inspired. We're honoured to have Aad's wife, Ms. Chris Lackey, with us here in person today, and other family members also joining us online. And on behalf of the Smithsonian Astrophysical Observatory, I extend my heartfelt gratitude to Aad's family and for their generosity in making this lectureship possible. It's now my privilege to introduce Dr. Stephen Cranmer, who will deliver today's Van Ballegooijen lecture. Dr. Stephen Cranmer is a solar physicist, and he specializes in the sun's corona, solar wind, and space weather. He's a co-investigator on NASA's PUNCH mission, which stands for those of you who are unaware, the polarimeter to unify, that is a capital U and a capital N, the corona and the heliosphere. It was launched in March 2025, and he leads Working Group 1C, which is focused on observing the Alphane surface in the outer corona. He's also a founding member of the Space Weather Technology Research and Education Center at the University of Colorado. He contributes to NASA's Parker Solar Probe as a co-investigator on the SWEEP and FIELDS instruments, which are transforming our understanding of the solar atmosphere and wind, and which is dear to our heart here because we have members of our community also working on SWEEP. He's an active member of the American Astronomical Society, American Physical Society, and the American Geophysical Union, and he previously served as associate editor for JGR Space Physics. He was a staff astrophysicist at the Center for Astrophysics, Harvard and Smithsonian from 1996 to 2014, so we overlapped for 3 years when I was a CFA fellow. Where he worked with the UVCS group on the SOHO spacecraft, studying ultraviolet emissions from the solar corona. Dr. Cranmer holds a PhD in physics and astronomy from the University of Delaware, a Master of Science in Astronomy from Ohio State University, and a Bachelor of Science in Physics from Drexel University. And today he's going to be telling us about interwoven paths and tangled fields, understanding the sun from multiple points of view. So thank you very much, Stephen, and we are looking forward to your talk.
All right, thanks. Thanks, Lisa, and thanks everybody for inviting me to give this talk. Yeah, it's been surreal coming back to the CFA after about a decade away. Some things are the same, some things are changed, but that's great. Yeah, I would love to start talking about some of the contributions that Aad made over the years. So yeah, so this talk is basically, I've sort of put together an outline where I'd like to talk about both observations, theoretical advancements, and numerical simulations, mostly with a focus on Aad's contributions, but also, so sort of, this talk hopefully will be sort of 50-50, you know, what are some of the most interesting new results in solar and heliospheric physics, and 50% just my highlighting some of the favorite things that Aad worked on over the years. and then ending up with sort of something of a synthesis. But yeah, the reason that I sort of went through these specific bullets, it's interesting to think about sort of where we've been and where we're going in terms of astronomy and space science and the studies of objects away from the Earth. Physics, for centuries and millennia, physics has had the advantage of doing experiments in the lab. But when we're studying these huge things that are, millions and trillions of miles away, we don't have the opportunity to do that. So for thousands of years, it's basically been just observing these distant objects. And when I say theory, I mean, again, for these thousands of years, it's been, writing down equations and solving things by hand. But of course, the 20th century, there's been a third pillar of science, and that's computer simulation, right? As computers have come along, they've really given us the opportunity to do virtual experiments inside computers that allow us to control the parameters of experiments like we do in the lab. So the goal here is to sort of investigate how all three of these things work together, and how really getting a full picture of the sun and the heliosphere really does now require sort of this multidisciplinary approach where we're looking at how all these different pieces interact with each other. So yeah, I'd like to start by talking about observations. The sun is a star, and it's the closest example of a star that we can see. I'm not going to say that it's the closest example of a star that we'll ever see. There are still some possible interesting concepts for interstellar probes out there that might be nice to get us a close look at other stars, or interferometric observations of other stars that might give us high quality observations. But for now, the sun is the star that we can see with the highest spatial resolution and also wonderful time resolution as we observe things change on the surface of the sun. We can also observe the different layers of the solar atmosphere by looking at different wavelengths in the spectrum. Throughout most of the visible spectrum, we see the solar photosphere, sort of the deepest layer that you can see with photons. And then other parts of the spectrum have opacity that allow us to look higher up in the atmosphere. There are certain spectral lines that allow us to see the solar chromosphere, where the temperature starts to increase a bit. The solar photosphere's temperature is about 6,000 Kelvin. The solar chromosphere goes up to about 10 to 20,000 Kelvin. And then there's this rapid jump to the solar corona, which has temperatures of 1,000,000 degrees. And the solar corona connects onto the solar wind, as we can see. I could even go back if you're curious, right? We can see it in solar eclipse images. You can see the solar wind start to pull away the material from the sun's magnetic field. And yeah, I always am interested in going back over the history of how we came to know that the solar corona was so hot. It actually goes all the way back to the 1860s, when people started to point spectrometers at the bright wispy light off to the side of the sun during a solar eclipse. And when they looked at the spectral lines in those spectrum, there were some that they could identify from existing chemical elements seen in the lab, and there were some that they couldn't. So for a while, for several decades, there was an idea of some new chemical element called coronium that might exist due to these unknown spectral lines. And it wasn't until about the 1930s that quantum mechanics was developed to the level that atomic physicists could actually understand the origin of those lines. They were actually lines coming from common elements, iron, nickel, calcium, I think also, but they were coming from highly ionized ions, right? So iron 10, iron 14, those basically have 9 to 13 of the electrons stripped away, and to maintain such highly ionized ions, you need temperatures that are extremely high, millions of degrees Kelvin. So this started the coronal heating problem, as it came to be called, because why would the sun that has a surface temperature of 6,000 Kelvin, it might be millions of degrees down to the core, but the temperature decreases as you go out from the core. Why would it suddenly increase again, to millions of degrees? That's the coronal heating problem. And in the 1960s, we got a much better look at the coronal heat by looking at images in the ultraviolet and X-ray, when we were able to launch space telescopes that could see above the Earth's atmosphere. So yeah, beautiful images of the corona. And this high temperature in the corona was seen in the 1950s to be connected to this thing called the solar wind. There was actually decades of evidence before that that there must be some sort of outflow from the sun into the rest of the solar system, because there were things that would happen on the sun, like a solar flare, and then a few days later, the Earth's magnetic field would be disturbed. But it was Gene Parker who realized that if the corona really is 1,000,000 degrees, it really must be in a continual state of expansion, continual state of acceleration. And my example of an overfilled balloon is really the same kind of thing. There's a pressure gradient. There's overpressure inside the balloon, much lower atmospheric pressure outside, and for at least the few seconds that it's releasing its air, there is a definite net acceleration from the inside of the balloon to the outside of the balloon. And that's what's happening continually. That's what he realized was happening continually in the outer reaches of the corona. This was controversial. His first paper on this was rejected and had to be negotiated a bit with the referees. But after 4 years or so, this was all happening at the dawn of the space age, and people were starting to send space probes out beyond the Earth's magnetosphere, and Neugebauer and others analyzed data from Mariner 2, and they realized that there really was this continuously flowing solar wind that fills most of the solar system with ionized gas. And since then, there's been many other ways of measuring it. This is a movie over here that shows a coronagraph. Hopefully it should repeat. It should be repeating, but anyway, there it goes. Yeah, this was a series of images taken with a solar coronagraph, essentially an artificial eclipse blocking out the sun, and then using some additional image processing to look at the fine-scale structure. But when the movie is playing, you're seeing there is continual outflow, that you can continually see stuff flowing out from the sun at all times, all the way around. The plot over here on the left shows what you can measure from spacecraft at 1 astronomical unit at the orbit of the Earth. This is 1 full year's worth of data of the solar wind speed, showing that there are times when it's a slow speed wind, sometimes when it's a high speed wind, and it varies, mostly having to do with the solar rotation. So yeah, this was confirmed. This is what we have. I did want to talk a little bit about where the energy for all this stuff comes from. I'm not quite getting into the theory part of the talk yet. This is still about observations. But it's important to sort of follow the chain back to where the energy comes from. There has to be some source of energy that heats up the corona. It turns out that the ultimate source really does come from the inside of the sun. There's actually plenty of energy streaming out through the sun, right? Anybody who's learned about the interiors of stars knows that there's nuclear fusion happening in the core, photons carrying energy out through the radiative zone of the star. In our own sun, those photons get absorbed, and the energy is then carried by randomly formed blobs of plasma where the hot blobs rise up and the cool blobs fall down, and there's a net transport of heat from the base of this convection zone to the top, and the energy flux, the watts per meter squared, is essentially, it's carrying the entire solar luminosity through that region, 63,000 kilowatts per meter squared. But by the time it gets to the surface of the sun is no longer convectively unstable. So essentially, most of this energy gets converted back into photons, and those photons escape. And that's what we observe as the bright sun, essentially. But at the surface, there is still a remnant of this convective overturning. And in fact, when we look at the surface of the sun, we see what looks like the top of a pot of boiling water. We're seeing the tops of those blobs that are rising up to the top. And the actual kinetic energy flux carried by these motions at the surface is just a small remnant. It's only about 500 kilowatts per square meter, but it's still a decent amount of kinetic energy that's being carried up at the solar surface. Now, as we go up from the solar surface from there, we have to think about the magnetic field of the sun, which is threading the surface. It turns out that only about 1 to 10% of that surface is connected up to those higher layers of the corona. If we want to figure out what type of energy is available to the corona, that only traces down to a small fraction, this 1 to 10% of the solar surface. So the energy that makes it up to the corona is only about 1 to 10% of that 500. But it turns out that this 5 to 50 kilowatts per meter squared is exactly what we need to heat the corona. So finding observations of this energy flux is important. We can observe it by looking at these, again, going back to the movie here, observing these magnetic structures, which are these little bright points in between the blobs. Those are where most of the magnetic field is living. And those are essentially threading the surface of the sun and being jostled back and forth. This is where Aad comes in, because back in the 90s, he worked with Pete Nissenson, and into the 2000s, he worked with Pradeep Chitta to come up with ways of measuring the motions of these small little features on the surface of the sun and convert those, essentially those random walk motions, into these kinds of upward energy fluxes that could then be used as the lower boundary conditions for models of coronal heating. So this is a cartoon we made of that whole process, how it zooms out, and this has been sort of a cottage industry in using high-resolution measurements of the solar photosphere to constrain this lower boundary condition. My own student, Sam Van Kooten, in 2024, extended this a little more. Rather than just looking at the centroids of these flux tubes as they're moving around and looking at the kinetic energy that carries, Sam also looked at the changes in shape of the cross-section of those tubes. They can either change in area or they become distorted, and those shape changes can also carry almost as much energy up as the jostling motions do. So with high-resolution measurements like from the DKIST telescope, we're able to track these things a lot better. And of course, I do want to talk about DKIST, and I'll show you an example of a recent movie of the solar photosphere. It's not showing great as going through PowerPoint and the projector, but if anybody wants to see a better version of it, we can look at it on the laptop. The DKIST telescope, of course, is a 4-meter diameter telescope in Hawaii that has recently begun some diffraction-limited observing, with the pixels in this movie are 6-kilometer pixels, which is just tiny, 8/thousandths of an arc second in size. That's not the actual spatial resolution. There's atmospheric seeing effects, all sorts of things. This is a region of the sun. Each one of these large things here are those rising blobs, those granules in the solar photosphere, and these are the lanes in between. This is a region of the sun where those lanes are completely filled with magnetic field, and you can just see some beautiful Kelvin-Helmholtz instabilities and beautiful leaf-like structures that are evident with this high resolution. So yeah, fascinating times for solar physics, trying to understand what's actually happening to the magnetic field at this level. All right, plenty of things to talk about. I do want to actually zoom out to a slightly larger scale, because in addition to looking at the lower boundary conditions for coronal heating, we can see the results of the coronal heating as we measure the temperatures higher and higher up in the solar atmosphere. And I'll show you a plot of what those look like, but just to say that as you get higher and higher up in the solar atmosphere, the density of the gas goes down, and that means that the rate of particle-particle collisions gets lower and lower. Essentially, they become more and more rare. And that means that the gas is no longer in thermal equilibrium. And that means that the different components of the gas, things like protons, electrons, and the heavy ions that are left over after they've been ionized, are no longer at the same temperature. They can all carry different temperatures from one another. This is an example of that. This is now the temperature as a function of height above the solar photosphere on this weird logarithmic scale. We can see in general the chromosphere, the rapid rise to the corona, and then going out into the solar wind, right? The orbit of the Earth is at 200 in this scale. Spacecraft like Helios and Parker Solar Probe and Solar Orbiter are exploring the inner heliosphere. Ulysses and Voyager explored the outer, and the plasma escapes. The heating goes on and on, even all the way out into the solar system. Because if the heating were to have stopped at any point along these radial distances, the temperature would drop off as essentially a radius to the minus 4/3 power, and that would look sort of like this. But the fact that the temperature is staying steady and is dropping at a more shallow rate than that means that there is continuous heat being generated and keeping the gas warm. And again, it's keeping the gas warm in a way that the protons are always 2 to 3 times hotter than the electrons, and the heavy ions are hugely hotter than both the protons and the electrons. In fact, in the corona, the heavy ions get to temperatures of 100 million degrees or so, which is even hotter than in the core of the sun, which is only 15 million degrees. So yeah, a lot of interesting results that we can put together, including some most recent observations from Yemi Rivera in Solar Orbiter, just coming out earlier this year. So Aad was involved in a lot of these things. Aad was definitely involved in the UVCS mission. This UVCS and its predecessor Spartan were UV spectrometers that occult the sun, so basically create an artificial eclipse and then look at the UV spectral emission lines that are formed off to the side. This was John Cole's group at the CFA throughout the 90s and early 2000s. An interesting bit of history. Aad was also one of the original programmers for both the UVCS flight and ground software and the UVCS data analysis software that has been used by generations of solar physicists to process the data from this instrument. So if you came here wanting to know about Aad's scientific achievements, there's also Aad the vibe coder as well. So plenty of interesting contributions. So yeah, throughout the time I was here at the CFA, after the UVCS first results, we also realized that a next generation UVCS type instrument would be something that would really help answer a lot more questions. And our group were involved with at least 6, I think, multi-year proposal and concept study efforts from the 90s to about 2013, and then some additional ones at NRL. Anybody here who's familiar with those will get flashbacks to seeing some of these pictures from those efforts. Yeah, we never actually got a final instrument build out of that, but I still think there are good chances that future proposal efforts will be successful. So in addition to the UV spectroscopy, there was also broadband visible light coronagraph instruments on many of these proposed instruments. It's nice to have both the visible light and the ultraviolet together on the same mission. The visible light gives you information about by using linear polarimetry, you can get the coronal electron density very, very well from those observations. And Aad found an interesting way in about 2007. Aad, with Larry Gardner, worked out a way to take one of those broadband visible light coronagraphs and include one extra optical element, which would be a very much nicer than this one shown here, a nice calcite crystal, which has birefringence, and use the optical properties of that to measure the linear polarimetry that would be caused by small Doppler shifts, basically motions coming towards and away from the telescope. Despite not having spectroscopy in this instrument, you could actually do Doppler shift measurements with this calcite birefringence. We never got a chance to build that instrument, but it was a fascinating concept. All right, so yeah, I wanted to say a little bit more about the inner and the outer heliosphere measurements. Of course, the last decade has been the decade of the inner heliosphere frontier. Parker Solar Probe and Solar Orbiter were launched now a few years ago and have explored a lot about the inner heliosphere. This is just sort of a summary of some of those discoveries. Parker Solar Probe discovered these so-called switchback regions of magnetic fields measured with Parker Solar Probe. Parker Solar Probe also has side, not through the heat shield that protects it from the sun, but off to the side, and they've measured coronal mass ejections and lots of interesting things in the inner heliosphere, in the corona essentially. And Solar Orbiter also has many in situ instruments, and also recently Silvio Giordano published a paper with some plenty of interesting things happening there. Yeah, okay, that was my whirlwind tour, I guess, of observations. I did want to talk now about theory, right? Specifically on the more analytic paper and pencil theory. So I've got Aad the Young Turk here because there's some interesting stories from the 1980s that will come out here. So yeah, we have some top-level questions, right? After we observe all these things, we have questions, right? How is the sun's magnetic field structured, and how does it evolve in space and time? And then, of course, the big one, right? How is the corona and the chromosphere and all these other regions heated, right? This is my picture of the temperature as a function of distance. Right? We have the chromosphere, we have the rapid jump to the millions of degrees in the corona, and then the solar wind. How does that actually happen? What are the physical processes responsible? And of course, there's the why do we care type questions, right? For the evolution of the sun's magnetic field, I think there's a lot having to do with space weather forecasting there, because you really need to know exactly what the sun looks like at every minute in 3 dimensions as it's rotating past you, and that tells you a lot about the dangers that it sends our way. It's also important to know the origin of the coronal heating for space weather forecasting also, but I think there's also a more sort of idealized, physical understanding type thing that it's its own reward. That's why we study these things. Okay, just to start with that magnetic structure, where does all that structure come from, right? As I go back, there's a whole lot of complicated looking magnetic field structure, both on the small scales and the large scales in the sun, and the question is, where does it come from? There are some models out there that have the solar interior creating complex twisted fields, and then those fields rise up through the surface. But many other ideas are that the field inside the sun is much simpler, and then all that structuring happens only after it emerges above the solar surface. So if the solar interior only produces these simple sort of bipolar, essentially magnetic dipoles that emerge above the sun's surface, then the question is, how does the sun make it complex? How does the sun produce the twisted and tangled and braided magnetic fields that we eventually see in active parts of the corona? This is one of the things that Aad worked on in the 1980s with Pete Martins, and then later on with Sarah Martin as a part of some of these International Space Science Institute teams throughout the 90s. Van Ballegooijen and Martins 1989 is Aad's most cited paper at 834 citations, and it proposed this mechanism of shear as a way of creating twisted magnetic fields, even though you just start with simple bipolar magnetic fields. But if the regions of the solar surface that you're emerging into are also moving in different directions and shearing against each other, the magnetic field reconfigures itself into these more helical twisted shapes. Everyone seems to show this cartoon from their paper, but they also developed a very advanced mathematical model that was quite complete in describing how this structure evolves also. All right, so once these complicated structures form, we can also observe them, and of course we see things like twisted and tangled fields in prominences and filaments. Prominences and filaments are really the same sort of thing. When you see them as dark absorption features projected against the sun's surface, we call them filaments. When we see them off to the side as emission features, we call them prominences. And these have evidence for all this twisted, tangled, flux rope type structures where the magnetic fields are quite complicated. Yeah, it was interesting. Every few years, Aad would be sort of be getting bitten by a bug that I called the dextral versus sinistral barb bug, because you can see when you look at these filaments over here, when you're following the magnetic field, sometimes the barbs go off to the left, sometimes they go off to the right, and those are called dextral and sinistral, left and right-handed. And every few years, he would jump back into that field and develop some new ideas. It was really cool to see how the papers evolved over the decades when those models were brought back. There was one example of that in the mid-2000s when Aad developed a mathematical approach to essentially build up the complexity of these twisted structures from much simpler building blocks. This is a theme that will come back again and again, basically looking at the linear eigenmodes of a linear force-free field. Say, for example, in a cylinder, those linear eigenmodes would then be Bessel functions. and basically build up complexity that way with occasional deviations to allow for other physical processes, like the fact that gas can sometimes weigh down the field when you're in a gravitational field. Yeah, I just found a nice cartoon from one of his notes that eventually developed into one of these linear eigenmode type. I often think of these as sort of construction set models where they're based on simple analytic solutions, but you need a computer to essentially come up with the full realization and eventually model the density of these structures, much like what we see in the actual prominences. Yeah, this went back to work with Eric Priest and work with Ying-Na Su and others in the 2000s. Interestingly enough, in 2005, he and I began to develop one of these models to model ultra-relativistic galactic jets coming out of active galaxies. And since then, this is a much more recent picture that I found online that shows the twisted and tangled fields that are believed to be in those jets. Neither of us had time to finish it, but it was an interesting exercise to learn about those other kinds of systems. All right, these are the small-scale fields. There's also the large-scale magnetic fields of the entire sun, the global-scale magnetic fields, right? We can measure the magnetic field at the solar photosphere. It's a much more difficult thing to measure the magnetic field up in the corona. So what is typically done is this extrapolation idea. Essentially, you take the measured magnetic field on the sphere of the photosphere as the lower boundary condition and use something like Laplace's equation to extend it out, assuming it's a potential field. This potential field source surface method is a common method used in space weather forecasting. The problem with it, though, is that when you look at the magnetic fields that such a model creates, it's hard to see in some of these visualizations, but the field isn't quite realistic. It doesn't quite agree with the much more wispy and pointy shapes that one sees in total eclipse images. So Aad worked for a while on some models together with Anthony Yates, Leonard Strawn, who's here, and developing some better semi-analytic models, again with this idea of building block eigenmodes, but not quite this solving the same Laplace's equation that's being solved for the potential field model, that include the effect of the solar wind in some way in producing those much more wispy structures. Yeah, I'm also working with another student, Daniel Mendoza, who's working with a different strain of these models that was published by Rice and Yates in 2021 in trying to figure out what are the best parameters in such a model that would best match the total eclipse observations and thus improve space weather forecasting too. All right. I wanted the second of the big two topics of theoretical ideas was essentially this coronal heating problem. There's been decades of study over this, right? Is the heating dominated by waves? Is it dominated by slow braiding of the magnetic fields that occasionally dissipates through little bursty nanoflare explosions? Or is it something in between? Is flux emergence from below important? There was an interesting early debate in the 80s. Parker back in the 70s had this idea of topological dissipation, where he came up with this idea that this slow braiding of the magnetic field, showing with a cartoon something like this here, would eventually result in these little bursty nanoflares, even without magnetic resistivity. So essentially an ideal, pure vacuum magnetic field, according to Parker, would result in dissipation. Aad, in one of his first papers after his PhD, came out and said, "Nope, Parker, you're wrong. That's not how it works." And after a few papers back and forth, I think the consensus is now Aad was right. You really do need magnetic resistivity, essentially microscopic collisions that allow the magnetic reconnection to happen on small scales in order for this braiding model to actually work. So now, of course, there's been several other generations of models. One overall concept that I think is coming to dominate coronal heating theory is MHD turbulence. Right? Turbulence is this idea that if you're stirring your pot of coffee and there are spontaneous little structures that form in the fluid, as I've tried to illustrate here, and this spontaneous formation of smaller structures can be thought of as a cascade of energy from the large scales to the small scales, and as things get smaller and smaller, eventually it reaches a place where it dissipates and randomizes and produces heat. And that's where the coronal heating seems to come from. So this turbulence idea is actually a hybrid of the wave models, because Alfvén waves seem to be the overall carriers of these packets of energy. But then on the smallest scales where the heating actually happens, it's something much more close to these old braiding models. In the parlance of the 1980s, these wave models were called AC, alternating current models. The braiding models were called DC because they were much slower in terms of their energy buildup. And the turbulence is sort of a hybrid between the AC and the DC models. And there have been plenty of explanations of that. Last year's Van Ballegooijen lecture by Gary Zenk talked a lot about that. And I, just as a summary of the current state of the art, I wanted to show a few different simulations of coronal heating. So MHD turbulence is a successful ingredient in many modern day simulations, both the global kind, which can predict the overall three-dimensional structure of the corona from people like Zoran Mikic and colleagues, and then there's sort of more explicit models of turbulence in more restricted geometries, as in the models of Munehito Shoda and others. Yeah, it's been a very successful explanation for coronal heating. It's still not the solution to the coronal heating problem, but it's a very promising one. The way that Aad came into it was with some models that I've been calling the braid code since about 2011. But we got along for a few years using what are called phenomenological models of how turbulent. If you have a paper and pencil model of the turbulent cascade from the large scales to the small scales, you can estimate how much heating it would give you. It in the paper and pencil to a computer and let it evolve in time. And yeah, this is another one of these things where we initially looked at cylindrical contours. So these Bessel function eigenmodes were the basic building blocks of the turbulence. I always thought of this as the peppermint diagram, because some of these looked like peppermints. Yeah, this was a code from, let's see, where is it? Yeah, from 2011 with Ma and Ed and myself. And there have been subsequent variations on this model from Mitch Berger, Mike Hahn, Lauren Woolsey, and others. The first code was in IDL, but it was interesting in this 2011-2012 time. Aad taught himself the parallel processing and message passing interface aspects of Fortran 95 in order to produce a much more speeded up version of the code, which was very beneficial. And let me show the movie again, because again, once you put all these linear eigenmodes together, you can get very complicated stochastic turbulent structure in models like this. Yeah, there's been a lot of other ways of trying to prove that turbulence is actually what's heating the corona. Another way of doing this, and I think another point for MHD turbulence, is to model the coronal heating as a very abstract parameterized thing, which I've sort of tried to express here, essentially modeling the coronal heating as the Poynting flux coming up from the jostling motions, distributed over a coronal loop of a given length, and then multiplied by a dimensionless efficiency type factor that depends on the time scales and the spatial scales of the problem. Don't worry about what many of the symbols mean. These m and n exponents are interesting because many of the published analytic solutions to the coronal heating problem, proposed solutions to the coronal heating problem, can be boiled down to specific choices for these exponents m and n. So for example, those DC foot point stressing models sort of live in a specific part of this mn parameter space. The wave models are over here, the turbulence models are over here, other type of models like Taylor relaxation are over there. I've been investigating some imbalanced turbulence models that seem to fall along a specific diagonal line. Some of the numerical simulations can be, you can back out values of these exponents into a box like this. And very recently, I've been working with the postdoc Chris Gilley on sort of an old idea that was pioneered by Carl Schreiber in the early 2000s, then later on by Lorraine Lundquist, who was a postdoc here at the CFA later on in the 2000s, in basically simulating the emission from the EUV and the X-ray multiple filters that we can observe from things like AIA and XRT, and running these models with all the different possible combinations of M and N, and just finding the best values that agree most with the data. And these black points are my current estimates. This paper is still being written, and it'll be submitted soon, but those are our current best estimates for where the data actually seem to fall. And it seems to fall along this line that describes imbalanced MHD turbulence. So I think this is a preliminary piece of evidence in favor of the turbulence explanation of coronal heating. Now, it's not always the case that one model rules them all. There are other places, and specifically in the twisted magnetic flux ropes in active regions, where something else might be happening. And in 2008, Aad got this idea that even though most of this coronal heating is describable as a kind of a diffusion of energy, essentially, if you start off with energy, it will then sort of randomly diffuse. It'll be like, molasses or something that spreads out. And that's describable by a second-order differential equation called the diffusion equation. Aad realized that in these twisted magnetic regions, there's a specific type of relaxation of that magnetic field that obeys a different differential equation, a fourth-order differential equation that's often called hyperdiffusion. That was a surprise because one doesn't often see applications of fourth-order hyperdiffusion equations in real physics. But this seems to be one application where that actually happens. And I just sort of illustrate what happens to a feature that diffuses using classical diffusion versus hyperdiffusion. It's some interesting math, and this was a very odd concept because he found some very interesting math that explained something in a new way. Anyway, all right. So that was my whirlwind tour of the analytic theory. There is a lot to say about numerical simulations too, right? Can we actually employ these large-scale simulations to forecast space weather? And this can go all the way from the interior of the sun all the way to the exterior. So in the interior of the sun, there's the solar dynamo. And in 2008, Aad actually built a full working model of the solar dynamo. He never published the thing. He talked about it at a few conferences. He worked with Duncan Mackay and Anthony Yates on this. But he actually built this full model of the 11-year solar cycle from, again, it's a construction set idea, right? Using the idea of models of individual active regions as they emerge through the surface, and then using what we learned from individual simulations of active regions and then plopping them in at the right rate, you can actually build up full-on models of the 11-year solar cycle to produce a realistic dynamo. All right, that's the inside. What about the surface, right? At the surface of the sun, we see the magnetic elements moving around, right? We talked about the magnetic flux tubes being jostled back and forth. On slightly larger scales, you can see these positive and negative, the salt and pepper magnetic field elements being jostled around. They emerge from below the surface. They merge or cancel with their neighbors. Sometimes they disappear by dropping back down below the surface. And in, I guess, the late 90s, with Carl Schreiber again, they worked on a model that was called magnetochemistry, essentially looking at the evolution of the magnetic field as the sum of a large number of these random interactions of emergence, merging, canceling, subduction, all these things happening at once. And it's only by plopping them all into a simulation and seeing the emergent behavior that happens on much larger scales, it really does require simulating the whole thing rather than trying to come up with equations to tell you what happens. One of the conclusions from that was that the idea of supergranulation, which I haven't talked about, which is a much larger scale, 30 times bigger than the granules that's often seen. Many people assume that those supergranules are also convective elements that are just happening on a larger scale. But in some of these magnetochemistry models, the supergranules emerged naturally just from the random interactions between these smaller scale magnetic elements. So it might on the supergranular scales. yeah, Aad worked with Carl. He worked with postdoc Karen Meyer, who I think started off in the CFA REU program, and with Duncan Mackay, Claire Parnell, and some others in the UK on these types of models. And yeah, we learned a lot about these kind of things. But we can even go up into the atmosphere from there, right? From the photosphere, chromosphere, right? What about the chromospheric heating problem? Where does the energy come from there? You know, we talked about the photospheric magnetic elements are being jostled back and forth. Those earlier models I talked about sending the wave energy up into the corona, essentially assume that this jostling takes place in a vacuum and the alphane waves propagate up as in an ideal system. But that's really not, they're really not in a vacuum. These magnetic elements are embedded in a surrounding partially ionized gas of the chromosphere. So 3D simulations really are a place where an environment around the beta equals 1 surface, where magnetic pressure and gas pressure are sort of equally strong and fighting against one another. You really do just need to simulate the whole thing. Aad worked with Hank Sprout earlier in sort of characterizing the types of interactions that can happen to these flux tubes, and then later with Siraj Hassan in building up simulations of how does the magnetic field interact with the surrounding gas. And in fact, when these magnetic flux tubes are jostled back and forth, they actually excite these pressure pulses that can propagate up the field and produce some other aspects of what we observe with Doppler shifts in the chromosphere as well. All right, again, this is just a whirlwind tour of all sorts of things. We're still going up into the corona, and as we try to look at the organization of the coronal magnetic fields, it's very complex. This is another field where direct simulation is important. So Aad in 2004 proposed a way of modeling the magnetic fields in the corona. Again, this is a place where we can't directly measure the magnetic field, but we can see the shapes of the magnetic field lines. We often see these S-shaped sigmoid active regions. And Aad proposed this idea of inserting some non-potential flux into a potential simulation and then allowing it to evolve to a steady state via this magneto-friction concept. And this led to this so-called coronal modeling software that has now been used. This is just a picture of the solar stellar X-ray group here that's been using this model for several decades to produce more realistic models of the early stages of flares and coronal mass ejections. All right, that's a lot. So yeah, I wanted to get down to the synthesis level. I only have one slide on synthesis because we've talked about observations, we've talked about theory, and yeah, one of the things that I always admired about Aad was that he always knew what the right tool was for the job, right? And some of these things are kind of an art, more of an art than a science, right? Out of all the different observations that are made, which are the ones that are really important? Which are the ones that help us distinguish between different explanations, right? How do you know what new data are needed to fill in the gaps, right? This calcite crystal idea would have been a nice way of gathering some new data that couldn't have been done any other way. And then, of course, in theory and simulations, which types of tools do you apply to a given problem when you have questions, right? And I just want to say, despite the many simulations that Aad designed and ran and developed the software for, I definitely ended up learning a lot more to treat these numerical tools only sort of as the object of last resort, right? Only after better options, which I would call analytic theory as a better option, after that's been exhausted, then you go to the simulations to really see how the complex system works. But there's so much you can learn from the much more simple traditional options, I think. Anyway, I guess that's it. Yeah, the big coronal heating problem and solar wind acceleration problems are still around. They're not yet solved, but I think we're including more and more real physics in these models, and I think those models are now doing better at explaining what we see and guiding how to make the next generation of observations as well. Yeah, I'd always kept an eye on the 3 pillars that I talked about at the beginning, plus a 4th pillar that I don't think should ever be neglected. And I think our science and our lives are so much the better for it. All right, thanks.
Thank you for that. another excellent lecture, Stephen, and now to questions. Okay.
You need the mic?
For those who are online, you need them.
Okay. Steve, why the hell did you leave the CFA? Now, that was a great talk. Thank you for this beautiful overview.
Thanks, Ramesh.
So I had only kind of one, I mean, there are lots of questions I have, but I'll ask one. So you talked about this imbalanced turbulence as the source of heating. And my picture of that is just oppositely oriented alpha-n waves, basically, in this magnetic structure, right? Now, the thing that kind of surprises me there is you talked about heating happening out to the Earth's orbit and even beyond from the data. Whereas I would have thought by the time you come out so far, there are no returning waves. There are only outgoing waves. So how can it still be operating?
Interestingly enough, when you measure that imbalance ratio going out into the solar system, it actually becomes more balanced the further out that you go. And it's scale dependent also, because when you go to smaller and smaller scales, they don't know about the more distant things that are happening. So on the smaller scales, it becomes mixed up, and it doesn't even know the background field direction anymore, really. So it's much easier to become balanced on tiny scales.
Still, the Poynting flux is going one way, right? Yeah. Somebody has to reflect it.
Well, but there's an overall radial gradient in the alphane speed, and when you have waves propagating through an inhomogeneous medium with a change in the gradient, it's almost like propagating into a wall. There's reflection and refraction, but it can just happen more gradually with an overall gradient. Yeah.
Charles, you had a question?
Yeah. So thank you very much, and thank you, Ramesh, for making that key point.
Charles, your fault.
Yeah, oh God. Moving right along here. There's a lot of interest in the work of a lot of people on exoplanets in this room. And one of them has been dealing with how troublingly active very much lower mass stars are. Does that grow naturally out of any of these theories, or are these theories just something for the sun?
Yeah. We've been trying to take what we've learned from the sun and apply it to other stars. And you know what? You've actually spurred on an extra slide that I have. Because if you look at, say, the mass loss rates of stellar winds across the HR diagram, that's what's plotted in the colored points here. When you look at the sun and other stars down to the M dwarfs and up into the red giants, we can measure a lot of mass loss rates. And we can actually do a good job with solar-inspired MHD turbulence models. This paper with Steve Sarr, I don't know if he's around, from 2011, I think did a good job with that. One problem, though, is that even though these models can predict the mass loss rates of the winds, they can't yet do a good job on the X-ray and other emission of the coronas of those winds. M dwarfs have way too much activity than what you'd expect from models like this. Essentially, these models take that, sigma T effective to the fourth from the surface and take some fraction of it and put it into the heating. M dwarfs have much less sigma T effective to the fourth than other stars, but their levels of solar activity are much more efficient, and we're still trying to figure out how that works.
Question down the back here.
So an interesting result that actually came out of the CFA back in the 1970s was that sunspots, which have the strongest and most extended magnetic fields, have by far the coolest corona. So there was some consternation because there was such enthusiasm for linking magnetic heating that MHD turbulence is suppressed in sunspots. Is that right?
Yeah, that's, I think, one of the things that's happening. I went back to this because the V perpendicular in these models, which is also hidden somewhere in there too, is the amount of jostling that's happening at the foot points in the photosphere. And once the overall flux density gets to be bigger than about a kilogauss or so, that of large scale flux density, I forget the details, but
the most obvious discriminator between the sunspot fields and those all over the rest of the sun is not so much intensity, because the small flux tubes are also very intense, but they're at the spatial scale. So that, I think that if I were modeling it, I would highlight that aspect of it.
Okay. Another question at the back.
So what do you think we need most in order to solve the coronal heating problem?
Oh, gosh. Money, yeah, that's right.
If money were no object.
You know what? The observations are in a pretty good state. I mean, I still think that there are places where there are big gaps. You know, we could use a next generation UVCS type instrument. More spatial resolution is always a good idea. People power, I think it might be our limiting factor in some ways, that there are just so many ideas that we want to test out and try out, and sometimes we need more people.
Hear, hear. Okay, well, I'd like to thank Stephen again, and also join me in thanking the Van Hooyen family for very generously endowing this lecture so that we're able to hear wonderful solar astronomy speakers like this, as well as honouring the legacy of Aad, his science, and also his mentorship. So thank you very much.